Hey, welcome back, everybody. Okay, so let's go ahead and talk about how hydrogen atoms make transitions, and we'll do an example problem. So I'm going to refer again to this energy level diagram. This just shows, in this diagram, the first four energy levels of the hydrogen atom using the Bohr model. So again, we have energy on the vertical scale. Going up is towards more energy. So the ground state, n equal 1, is minus 13.6 eV. The first excited state, n equal 2, minus 3.40 eV. N equal 3, second excited state, minus 1.51 eV, etc. And we're just using this formula right here to generate those energy levels, minus 13.6 eV over n squared. Now, the way we figure out photon energies and wavelengths with transitions is we remember that, and you can see this on the next page, a photon is emitted when the atom makes a transition from a higher level to a lower level, a higher state to a lower state. Okay? The reverse process, going from a lower level to a higher level, that's going to be when a photon is absorbed. Okay? Now, the difference in the energy levels is going to equal the photon energy, whether it's emitted or absorbed. So if you want to figure out what is the energy of the photon that is emitted or absorbed, just take the difference of the two atomic energies that are key in that transition. And what I suggest is you just subtract the two energies, atomic energies, and take the absolute value. Now, don't get the photon energy confused with the atomic energies. I'm referring to the atomic energies with the subscript NF for final and NI for initial. That E sub N is my reminder. I'm talking about the atomic energies, which are minus 13.6 eV over n squared. The photon energy I always am going to denote with a pH subscript. So I always just take the difference between the two atomic energies, absolute value, and that's the photon energy, whether it's emitted or absorbed. Don't forget also that these energies, these atomic energies, are negative. They're all negative. So you have to be careful when you're doing that subtraction. Okay? And then once you know the energy of the photon, you can get its wavelength by just remembering that the energy of a photon is hc over lambda naught, or 1243 eV nanometers over lambda naught. So if you know the photon energy, you can use this equation to get the wavelength, or vice versa. You may be told that a certain wavelength is absorbed by the hydrogen atom, and you have to figure out what the energy of the photon is. Okay? All right, so let's do a numerical example right here. Okay, and I'll do it in the notepad, but look, you can just read it right here. Find the wavelength of the photon emitted when a hydrogen atom makes a transition from the second excited state to the first excited state, and what part of the spectrum is the photon. And then find the wavelength of the photon absorbed if a hydrogen atom goes from the ground state to the first excited state, and what portion of the spectrum is the photon. Okay, so let's go ahead and do A. We're going to go, the atom's going to go from the second excited state to the first excited state. Okay, so what that tells me is that, so this is the example problem. This transition is from n equal 3 to n equal 2, right? N equal 3 is the second excited state, and n equal 2 is the first excited state. So then all I have to do is I say, okay, and I have to figure out, again, I have to figure out the wavelength. So I'll first figure out the photon energy. Okay, so the energy of the photon is just going to be the difference between the final state, that's E2, minus the initial state, which is E3. Okay, so I can just use this formula, right? I mean, if I have the diagram already made with the first 4 or 5 states labeled, I can just use that directly. But I can always use this formula to figure out the atomic energy for a given quantum number n. So if I punch my calculator, I'll find out that E2, right, I put 13.6 over 2 squared, and I'm going to get minus 3.40 eV. And if I put 3 in there and square it, I'm going to get minus 1.51 eV. And again, if you have an energy level diagram already made, like you see here, you can see that. Okay, so I take the difference between those two. So my over here then, my photon energy is going to be the absolute value of minus 3.40 eV minus negative minus 1.51 eV. Again, pay attention to those negative signs. So that turns out to be 1.89 eV. And I know this photon is emitted. Now, if I want to know what the wavelength of that photon is, lambda naught is 1243 eV nanometer over the energy of the photon. You see how convenient it is to keep energies in eV and wavelengths in nanometers. Okay, so we just get 1243 eV nanometer over 1.89 eV. And if you punch that in your calculator, you're going to get the answer of 656 nanometers. That's the 3-to-2 transition. So that ends up equaling 656 nanometers. Okay, is that what I just, yes. Okay, and what part of the spectrum is that? If you go to our course page and look up the electromagnetic spectrum, free space wavelength, that's going to be red. Oh, in fact, look, let me show you guys. Remember, if we go to our course page, I was looking at this emission spectra. The top one is hydrogen. That's this right here. That's that red wavelength. Oh, and in fact, if the atom goes n equal 4 to n equal 2, that's going to give you the green line. N equal 5 to n equal 2, this blue. N equal 6 to n equal 2, this violet. In fact, that forms what's called the Balmer series of hydrogen. Historically, people were getting the emission spectra of different gases before they really understood what was going on with the atom. So the Balmer series was well known, and there were other series with hydrogen, also emission series. So what Bohr was able to do was say, look, boom, here is the Balmer series right in your lap. Okay? There were empirical relationships for this series involving something called the Rydberg constant, R sub h. You can Google that if you want. What Bohr was able to do, though, was say, oh, look, I have a reason for the emission spectra of hydrogen based on this theory. In fact, Bohr predicted certain emission series, certain wavelengths that people hadn't even looked at. And when they went to look at them, they said, oh my gosh, there are lines in the infrared and the ultraviolet that we didn't even know about. And they're predicted by Bohr. So Bohr's model, while it is simplified and has some flaws, it does successfully explain this visible emission spectra of hydrogen, the so-called Balmer series. Okay, what's the next question? Find the wavelength of the photon absorbed if hydrogen goes from the ground state to the first excited state. And in what part of the spectrum is this? Okay, so for this one, what we want to do is we want to go to from the ground state to the first excited state. So I should mention, I guess, if I'm using my energy level diagram in A, so what you could do is you could say, okay, this is n equal 1, and then this is n equal 2. And again, on the energy scale, these are not equally spaced. This is n equal 3, right? You could demonstrate this or show this transition from 3 to 2. People often will put a dot here representing the electron with a downward arrow and then a photon that's emitted in the transition. So that's how you could represent that. Let's do a similar picture for B. What we're going to do in B is we're going to look at an absorption process, though. So we want to go from the ground state, which is n equal 1, to the first excited state, which is 2. So on my energy level diagram, if this is n equal 1, this is n equal 2, right? Here's n equal 3. I'm looking at this transition. The electron is here in this state and wants to go up to that state. And it does it by absorbing the photon. Okay, now, again, this photon has to have the right energy. This is what's so cool about nature, right? If this photon doesn't have the right energy to get from n equal 1 to n equal 2, or n equal 1 to n equal 3, or n equal 1 to n equal 4, etc., that photon will not be absorbed. It will just go straight through that gas. Pretty neat. Okay, so let's do this. Now, the method here is the same. Once we know the final and initial values of n, it's the same process. So the photon energy that's absorbed in this case is going to be final E2 minus initial E1. So I just need to know what these are. So E2 is minus 3.40 eV, right? We know that from previously, minus 13.6 eV over n squared. E1, the ground state, is going to be minus 13.6 eV, if you put n equal 1 in that formula up there. So I take the difference of those two. So again, what's your minus sign? So minus 3.40 eV minus negative 13.6 eV. And if I do that difference, I'm going to get 10.2 eV. So that is the energy of the photon that's absorbed. And then to figure out the wavelength of that, the free space wavelength, I just take 1243 eV nanometer, and I divide by the energy of the photon, 10.2 eV, and I will get the wavelength in nanometers, which turns out to be, I think, 121. Let me double check. About 122. Yeah, I don't have a calculator that I'm actually calculating this with, so I'll just correct that. About 122 nanometers. Now, where is that in the spectrum? Again, you can call it up on our course page or Google it. Free space wavelength of 122 nanometers. That is an ultraviolet photon. In fact, if an atom is in the ground state, it cannot absorb a visible photon. We just proved that because look, the smallest energy that this atom can absorb, if it's in the ground state, is when it goes from n equal 1 to n equal 2. Any other absorption transition is going to require more energy in the photon. So the smallest amount of energy that it can absorb is going to be this ultraviolet photon. Visible photons have less energy than ultraviolet, right? Visible photons have longer wavelengths, therefore smaller photon energies. So a ground state hydrogen atom cannot absorb visible light. Now, a first excited state atom can. It can absorb a photon going from 2 to 3, a visible photon, or 2 to 4, or 2 to 5, or 2 to 6. The photons that it can absorb are the same ones that it emits, going from n equals 6 to 2, 5 to 2, 4 to 2, 3 to 2. So these same photons that you see up here in the emission spectrum are the ones that are going to get absorbed if you send white light through the gas. Okay? All right, so you can analyze different transitions with the hydrogen atom just using that energy level diagram, which comes from the atomic energy formula, minus 13.6 eV over n squared. You see that right here. You just take the difference between the atomic energies, absolute value gives you the photon energy, and then you can find the wavelength knowing the photon energy. Okay? A variation of a question, for instance, what I could ask you, like in B, this was the transition from 1 to 2. Another way I could ask B is I could say, hey, you have a ground state hydrogen atom, and it absorbs a 122 nanometer photon. what state does it go to? So what you would do is, if I give you the wavelength absorbed, you could figure out the photon energy using this formula. Once you know the photon energy that's absorbed, take the initial atomic energy, add the photon energy. That'll tell you what the final energy is. So again, that would look something like this. Let's go ahead and do it so you can see what I'm talking about. So if I gave you the wavelength, so if you know that the wavelength absorbed is 122 nanometers, so this is known, the first thing you would do is you would say, okay, and you also know that the ground state energy is, right, n equal 1, the atom is in the ground state. What you would do is you would figure out the photon energy first using the same formula. So you would put in the wavelength though, and you would find out that this is 10.2 eV. Then you would say, okay, look, the initial atomic energy, E1, is minus 13.6 eV. What I'm going to do, since the photon is absorbed, I'm going to add to E1 the photon energy, and that should get me, E sub n, that should get me the final atomic energy. Let me label that E n sub f, because you don't know what n sub f is going to be yet. So you would say, okay, minus 13.6 eV plus 10.2 eV, and now I'm sitting at an atomic energy that's equal to minus 3.40 eV. Now, once you know that, you say, where is that? Right? What is the n? Well, you just remember that atomic energies are given by minus 13.6 eV over n squared. So if you know that the atomic energy is minus 3.4, you should be able to figure out the quantum number n. And if you do that, you'll find out that that's n equal 2. Okay? All right, so you should know how to do the absorption process if given a wavelength. Okay? Or I could give you the wavelength that's emitted and say the atom is in, n equals 6 state. And it spits out a photon with a certain wavelength. What is the final quantum number of, right? What state does it go to? So again, what you would do there is you would figure out the photon energy, right? Since it's emitted, subtract that from the initial atomic energy. You'll know the final atomic energy, and then you can figure out the quantum number n. Okay? All variations of using this atomic energy formula and the fact that the difference of atomic energy's absolute value is the photon energy. And of course, the relationship between photon energy and its wavelength. Okay, I will stop there. Practice Bohr model of the hydrogen atom. And in the next video, we're going to start a new topic. Okay, bye-bye.